an application to image and video is started only by saying only one part, rough fuzzy clustering, that means pixel classification. That means given an image, I consider every pixel as an element or object or as a pattern, and I see in which part of the segments of the image it would belong. Because it is an unsupervised, therefore I do not know the number of classes, or I do not know which classes they are representing in the image. It is unsupervised again. So it is a segmentation, means a clustering. That means I have the entire image. My task is to assign every pixel element into one of the classes as determined by the algorithm or as just given by you as the number of classes. So if I give C number of classes, my task is to assign every pixel of the image to one of the C classes. And based on that, I get the different object regions. So this is unsupervised technique. Now today I'll go for this remaining portion, generalized rough sets and object extraction, then followed by video tracking. And here I will mention first the objects segmentation by your gray level thresholding. This is the difference. Here it was by pixel classification. There I will go by the given an image, I find its gray level histogram 0 to 31 or 0 to 8. Sorry, if it is a 32 level image, then 0 to 31. If it is a 64 level image, then it is 0 to 63 on something. So all these levels, and I will see in which part of the threshold I can partition. I can put a threshold, which part of the gray level scale, so that I can have different regions. So this is the difference I will explain. And here I will explain.
Sir, your screen is not seen.
Screen is not seen?
No, sir. Can
Why?
you please share screen? Can you please share screen?
Oh, so long you could not see my screen.
Yes, sir.
Is it now okay? No?
Sir, still not visible, sir.
Oh.
I think I'll also put my video off.
Oh, sorry. Now let's see you have now it is your. But when I click the sharing button, the arrow goes down, just like previous day. It was also happening. Can you please check at your end? When I click it, choose share tray.
So once you click that, you will get a box
Downward
of share
arrow.
screen.
When I click it, I get a downward arrow. Previously, it is an upward arrow. When I click it, then it becomes downward.
So there is no screen seen, share screen.
No, nothing. Yeah, screen see now. See if it is coming here. Can you now see?
No, sir.
It's okay now.
No, it's still not come, sir.
I don't know. In my other meetings, I do not have such problem. Why it is here? Share.
Now we can see, sir. Yes. Now again, I have.
Stop sharing. Open sharing. Screen share. Can you see now? No?
We can see your screen, but we can't see your presentation. You have to click on your presentation. Yes. Now, yes, sir.
Now
Yes.
it is okay?
Yes, sir. Thank you, sir.
Okay, okay. Goodness. I don't know what kind of link it is because I have never faced this kind of problem before. Okay. So let me start again from here.
Okay, sir. Okay, sir. No problem.
Please. So in my first lecture, I explained starting from soft computing, pattern recognition, machine intelligence, then fuzzy sets and flexibility, all kinds of rough sets, then artificial neural network, genetic algorithm, relevance to pattern recognition with examples of case mining up to lecture 1. And then second day, I lecture in details in granular computing, what is the constituting elements, concepts, then all kinds of integration under granulation model, then judicious integrations. Then I gave more importance to rough fuzzy computing because it is a strong uncertainty modeling paradigm. Then emergence of soft computing from this point, all kinds of integration. Then I explained generalized rough sets, all kinds of lower approximation, upper approximation, and the entropy measure. Then I took up to this an application of this image and video analysis. I only considered rough fuzzy clustering, which is an unsupervised classification algorithm. And here the characteristic that you consider every pixel in an image as an element or a pattern, and then see to which class out of C classes given without knowing their origin, without knowing their class level. Only I know that there are C classes given by 2. C could be 2, 3, 4, 5, 6. So my task is to assign every picture element to one of those classes. And in the process, as an output, I get different clusters, that's called segments, which represent different image regions of an image. It's an unsupervised. Now I will explain today. We start saying next one, the same segmentation based on gray level thresholding. That means if you have 0 to 31 gray level or 0 to 61 gray levels, then in which part of the gray level will constitute one region, which part will constitute another region, which part will constitute. Here, without knowing the gray level distribution, without knowing the gray level one, I didn't bother about anything distribution. But here I will see the other way. That means I do not go by the pixel by pixel, I go by the level wise. That means I consider every pixel and I see that in which part of the region it belongs. Then accordingly, I put it to that region. And here I will explain the significance of generalized rough sets, which I explained in my last lecture, that which is a uncertainty handling paradigm, uncertainty arising from granularity and uncertainty arising from overlapping concept, not arising from probability of occurrence of an event. Okay, so I will keep this in mind. You please keep this mind. And then I will ambiguity measure, significance of rough fuzzy entropy, its merit over fuzzy entropy, then effect of generalization, granule size. Then I go for granular flow graph. I will explain this for all with respect to unsupervised tracking. Unsupervised tracking, that I do not have any idea about the videos, what are the content in the image, but some moving objects are there. So I will try to track that image in an unsupervised manner. Then I will explain the role of different granular size. As I mentioned, in granular computing, size and shape of granules play an important role. So I will explain the granules of arbitrary shape, that means which is more natural. What I see in a scene is all arbitrary shape as compared to regular shape granules. Then I will explain the role of lower approximation. Lower approximation means definitely belonging to some object, definitely belonging to some set, definitely belonging to some class. And upper means definitely as well as possibly belong. So I will find the importance of lower approximation, how to extract from a video. Then I will explain the two-dimensional spatio color granule, three-dimensional spatio temporal granule, effective flow graph, Then I will explain the concept of rough filter, intuition entropy for unsupervised tracking in occlusion period. That means when it is completely occluded, overlapped, handling occlusion and overlapping. Then in a bioinformatics, I'll take one example because you wanted to know that its relevance to pharmaceutical industry. I explained in my last talk what are the ways, starting from R&D, starting from marketing, and starting from prediction, everything you can use artificial intelligence in pharmaceutics. So here I will explain in one of those examples in R&D, how to find microRNA selection and similar things so that it can be used for drug discovery. Then the last part is more important. It's a challenging issues. I'll explain. That is when you do some research work, you need to keep in mind where are they going to be used for the next 10 years, about 7 to 10 years. So I will say here its relevance to computational theory of perception, Z-number machine mind development, relevance to natural computing and big data analytics. Here comes the relevance of deep learning, because today when you talk about big data, data mining, it remains incomplete if we do not mention about deep learning. And what are the problems? Then the relevance of this granulated deep learning. And here I will explain a new recent work which has appeared this year, granulated region-based convolutional neural network, GRCNN architecture, video tracking, and its merit over RCNN, faster RCNN. Then at last, the evolution of the entire discipline from pattern to data science. And for young researchers who are joining to one, I will explain very carefully some caution and concerns that we don't expect much unless you contribute to this science. So far, in the last lecture, I have explained image partitioning by pixel classification. Now I will explain image partitioning by gray level thresholding. As I mentioned already, pixel classification means without knowing the gray level values, I consider a pixel and I find its similarity with respect to some centroid of some classes or some other way, I assign it to one of the classes. And here, I do not want to know the location of the pixel element. I go by the gray level. That means irrespective of the location of a pixel, I consider a pixel and let's see its gray value. If its gray value belongs to this 1 to 5 or it is 5 to 12 or something. So that is which part of the grayscale region that pixel intensity would belong. Accordingly, I find thresholded segmented value. So this I will explain here. I need to know the generalized rough image entropy. We have explained in detail generalized rough set. Now we'll use it for ambiguity measures in image analysis. And again, why we need granules? Because it determines the roughly resemblance of gray levels and pixels. So, and I will explain superiority of the rough fuzzy entropy over fuzzy entropy. That is the necessity of granulation. Necessity of granulation for segmentation problem. As I mentioned before, clustering and this image segmentation is an unsolved problem. And given any kind of data, if it is an image, you have to know how to make it best kind of segmentation, because you don't have any other idea. Just like clustering, it becomes a mandate for any scientist handling with data. When we started work in 70s, that was a subject for electrical engineer. Computer science did not come that time. Then computer scientists jumped over the subject, statisticians jumped over the subject, and subject was grown up. But today, it is a subject for any applied scientist dealing with data. So let me remind image ambiguity. Why rough fuzzy and rough fuzzy? Because regions in gray image have fuzzy boundaries. Because an exact boundary cannot be defined as a consequence of the presence of steadily changing gray levels, sinusoidal values. And why rough set? Similarly, nearby gray levels, that means 5 is close to 4 and 6, 6 is close to 5 and 7, 7 is close to 6 and 8, and so on. So there is a concept of rough resemblance of gray levels. And similarly, rough resemblance between nearby pixels. That means any pixel, picture element, pixel tends to attain its intensity value as close to its neighboring pixel intensity. So there is a concept of rough resemblance of nearby pixels, rough resemblance of nearby gray levels. And this make you, together with these fuzzy boundaries, that fuzzy boundaries of region plus rough resemblance between nearby gray levels plus rough resemblance between nearby pixels gives rise to concept of your rough fuzzy entropy. I will measure rough fuzzy entropy measure and I will consider rough fuzzy uncertainty measure for an image. So in rough set theoretic framework, defined objects can be described as rough sets with upper or lower approximation. That means outer or inner. That means with definitely belonging to the object region or definitely and possibly belong to the object region. Uncertainty. Whereas in case of fuzzy set theoretic framework, defined image segments, regions, edges, features, relation between regions, population of regions are considered as fuzzy subset rather than hard subset of the image space, and they do not lend themselves to precise definition. So this is the basic two differences. Please keep it in mind. Here, every element, every region, edges, boundary, they consider as a fuzzy subset. That is characterized by degree of belonging of an element with a membership value, which indicates its compatibility of an imprecise concept like edge, imprecise concept like region, inserted concept like segmentation, imprecise region concept like relation between region and so on, with the left, right, upper, above, this kind of, which are fuzzy properties. Whereas here, any object is or region is considered in terms of lower and upper approximation. Lower means definitely I'm sure, upper means I'm not sure. It has definitely as well as possibly. So, and there are two types of ambiguity measure. What is called grayness ambiguity, or is called spatial ambiguity in image. What is grayness ambiguity? It means the indefiniteness associated with deciding whether a picture element or a clump of pixels called granules is considered to be white or black. The machine understands only white and black. Now, uncertainty or grayness ambiguity comes because of the indefiniteness associated with the decision or taking whether a pixel can be considered white or black, or a clump of pixels, a granule can be called as a group. Here, indefiniteness is concerned with gray value and individual pixel or group value of pixels. That means indefiniteness comes from the fuzziness as well as granularity. But the main thing is that ultimately it boils down to indefiniteness concerned with gray value of an individual pixel or group of pixels. Whereas in case of spatial ambiguity, which refers to indefiniteness in shape and geometry, here it is indefiniteness associated with whether a pixel or a group of pixels is white or black. Here indefiniteness comes from shape and geometry. That means if I ask you that, where is the boundary? What is the boundary of these two classes? So this question leads to some indefiniteness in shape and geometry of variable. Here, indefiniteness concerned with both gray value and a spatial location of individual pixel and group of pixel. You keep this in mind always. Here it is only because of the gray value of individual and group of pixel, and here in case of gray value as well as location of individual pixel and one. So here it is more expensive, but it is more if you have more effective result solution you'll get from here, obviously, because here you are considering only intensity value. Here considering intensity value as well as the pixel location. And here we will use the same the rough fuzzy entropy as I mentioned in my last lecture for computing this grayness ambiguity and spatial ambiguity. So just keep in mind, grayness ambiguity means which comes from the gray value, whether gray value should be considered as black or white, whether gray value of an individual pixel or gray value of a group of pixels together. Whether in case of spatial ambiguity, it is gray value as well as the location. So, and we will use this For example, this rough fuzzy entropy for computing grayness ambiguity and spatial ambiguity. And you keep in mind that what is this entropy signifying? It signifies or quantifies incompleteness of knowledge about the universe with respect to definability of the set or object one. And that means this is a measure gain in incompleteness. So I will try to minimize this entropy in order to maximize my gaining in information, because it gets gaining incompleteness. So if I go the other way, that means if I minimize it, so I am minimizing the gaining incompleteness. That means I will maximize the information. So for that, for grayness ambiguity and spatial ambiguity, as I mentioned to you, it depends mainly on the intensity value, and it depends both on intensity as well as location. Now, how to compute? Say, for example, one-dimensional granule, two-dimensional granule for computing grayness ambiguity and spatial ambiguity. So I will explain. So one-dimensional granule for grayness and two-dimensional granule for spatial ambiguity. This is my grayscale, 1 to L for the image. So I can consider 1 to 3 as my granule, crisp granule, 3 to 5, one granule. There will be same equal size of granules of size 2. This is called non-overlapping one-dimensional granule. Then for depending on the complication, depending on the uncertainty, degree of uncertainty you want to handle, the granules could be overlapping. That means 1 to 3, 2 to 4, 3 to 5, then 4 to 6, overlapping. Then 6 to 8, something. So it's called overlapping one-dimensional granule. This I can use for grayness ambiguity. In case of spatial ambiguity, this can be further as fuzzy membership. 1 to 3, this kind of membership function, it's called fuzzy one-dimensional granule. So I had crisp granule, I have explained overlapping one-dimensional granule, I have explained fuzzy one-dimensional granule. While we compute granulation, grayness ambiguity, that means I'm not considering any kind of location, only the gray value, 0 to 1 to L. Now for spatial ambiguity, let's consider the image itself. M by N image. These are my all pixels. So I can consider 3 by 3 window, 3 by 3 window, 3 by 3 window, 3 by 3 window such way. Discrete is called non-overlapping two-dimensional granule. That is 3 by 3 window, 3 by 3 window, 3 by 3 window 1. Then I can have the overlapping. I call it overlapping two-dimensional granule. So depending on your level of uncertainty you want to handle, depending on your how much accurate you want to result, depending on how much money you have. So overlapping two-dimensional granules. And similarly, now consider this as a simple case, how to compute this grayness ambiguity one. So let's consider this one, simple case. Simple case. 1 to 3, 3 to 4, 3 non-overlapping one-dimensional granule. That means I go by this one-dimensional granule. That means 0 to 1, 1 granule, here is a granule, whatever. That means it's a crisp granule. Crisp granule. But I consider say fuzzy set. So by my rough set concept, my granules are crisp, but set is fuzzy. Now, if I did not have the granulation concept, that is 0 to L up to this, and I got this fuzzy set, then for every intensity, I have a one-to-one mapping. Membership values. Let the membership value be defining the brightness of image level. Lower the values of this, it is brighter. Higher the values of N means it is what? Or you can call it darker one, depending on the image, what kind of image you have. So given this fuzzy set, if I do not have granulation, for every value of intensity, I can have a unique value membership. This is without granulation. This is I can use for fuzzy membership value. Now, when I have this granulation concept, then the same value here, which had membership value here, now membership value come down to a lower intensity. Because I explained before, any granule, it has membership value what? For every element, you take a membership value here to here, take the minimum lower, take the maximum upper. So now, for any value here, point, now its membership value for lower is here, upper value is here. So because of the granulation, now it has got two membership values for this set, fuzzy set, characterized by lower and upper. Therefore, fuzzy entropy, new value of a pixel is entirely dependent on its own gray value, not location. But in case of rough fuzzy entropy, mu value depends on the granule to which it belongs. Granule to which it belongs. And this makes the difference in my image segmentation. I will explain. And as usual, the lower and upper, they characterize together what is called rough fuzzy set of X. Here is X is a fuzzy set. Granules are crisp. So what do I do? For a given image, I change this membership value crossover point. I move this crossover membership value from here to here, and then I see for which membership value its entropy is minimum. So I did segmentation or addition. I minimize Granules ambiguity with respect to crossover point. Crossover point means the point for which membership value is 0.5, for example, here. So I change this crossover point. That means I change this membership function here, here, so on, and then I see for which value it has minimum. That means membership value of pixel is dependent on one-dimensional gray level to which it belongs. It is independent of pixel spatial location, and results are compared with fuzzy entropy, where membership value of a pixel is entirely dependent on its own gray value, and it is independent. So I can, if I take the difference of these thresholds, I can see that difference is better because of this granule, fuzzy granules. That is, the granules characterized by lower approximation and upper approximation. So here is an image. I take three kinds of image: a baboon image, brain MRI image, remote sensing image. So their images have different characteristics. You can see they have different histograms. Histograms means levels and just number of occurrence of each level. Okay. So, and I take granule W equal 6, that be 1 to 6, 6 to 12, 12 to 18, 18 to 24, so on. Because why I took W because as I mentioned in my previous class, W is called Weber's law. That means naked eye cannot discriminate 6 consecutive gray levels in an image. So that's why I can take 1 to 6 as a granule. Similarly, 2 to, so if I take in the disjoint granule, crisp granule, so 1 to 6, 6 to 12, 12 to 18, so on. Now we can see that rough fuzzy entropy, fuzzy entropy. Look at the image, how is changed. Rough fuzzy entropy, fuzzy entropy. It's a big change in information. So how much good information you have extracted. Here it is not much changed because it is already darker image, maybe one. And similarly, now if we go for other images, now you can ask me that how can we just quantify? Here I use the same beta index I explained last time in my class. The simple beta index, dB index, Dan index. What is beta index? Again, you keep in mind that the here numerator for a just fixed number of region C, that the fixed number of class C, we assume C equal to known 3, 4, 5, 6, 7. So given C, I can see that numerator is indicates the difference from the mean value of the image from the individual region intensity value. So this value should be more so that the class separability is more. And here the denominator should be small, because here for the in a same class I, I'm computing the mean value of nth value in the ith region. So this difference should be low, so that my region is homogeneous, and the numerator should be more, so that my classes are separable, they be heterogeneous. So larger value of beta for a given number 6 is desirable. And that's what I'm now computing: brain MRI image of galaxies, image of nematodes, so many, 50, 45 images. And red signifies fuzzy entropy, and blue is why rough fuzzy entropy. See that your beta index, blue is always except 1, here it is 2, and one more, I think here is 3. So in 3 cases, otherwise in 45, in all cases, blue, that means rough fuzzy entropy, gives better beta index. That means better segmentation. That means better extraction of information. So this shows the significance of granulation over just non-granulation. So now let's explain the effect of generalization. Effect of generalization. That means set X is crisp, as I mentioned before. This was a rough set by Professor Pavlov, where set is crisp, granule is crisp. Okay. Now, if I consider what are the cases? Simple case is case set crisp, granule crisp. Then other case is set fuzzy, granule crisp. Another case is set crisp, granule fuzzy. Another case is both set and granular fuzzy. That's what I explained. Sorry, generalized offset. So I can have this X crisp, granule crisp, X fuzzy, granule crisp, X crisp, granule fuzzy, X fuzzy, granule fuzzy. Effect of generalization. And I consider logarithmic gain function, equivalence results, and see the results of examples. This is a histogram of this image. At different cases, I can see that index value is increasing. That means generalization improves beta index value. So let's take another value where histogram. See, look at this. This is the histogram. That means your gray value and number of times every value has a. So it has a distribution. Here you see that here it's a good image. So it is a peaks are more or less distinguished. That means this is one region, this is one region, and this is one region. At least there are 3 regions out there. Each peak signifies one region around this. Here it is 2 regions, at least you can see. At least 2 regions are there. Object and background. Here it is, object has got 2 regions, background plus object. So here also you see that beta value, except this, 9.66, 9.76, 10.1. Here it is again same. So except this, generalization improves. So conclusion is generalization incorporating fuzziness in rough set leads to better object extraction with respect to obtaining homogeneous object background region. Better object means in terms of extracting homogeneous object and background region. And my beta index quantitatively validates the fact. Now again, I'm mentioning you, here we considered uncertainty arising from granularity in the domain as well as the overlapping between region concept. I am not considering uncertainty arising from probability of occurrence of elements. Now let's come to, so far we have considered granules of equal size, right? W equal to 6, I consider. But in real life problem, it could be usually unequal size. So now let's see the effect of unequal size granule over equal size granule. Obviously, unequal size granule will give better segmentation because you are paying more and you are going by the natural granules. You are not assuming the granules are of equal size or shape. So here comes the formation of unequal granule and special segmentation. There I went for variable segmentation. Now here I'm coming for special segmentation because I'm using unequal granules in the two-dimensional plane. So I will explain the special ambiguity measure. Crisp set and crisp granule, I am considering simple case. Granules formed by a quadrate decomposition. I will explain quadrate decomposition, effect of granules of unequal size versus fixed size. Now, what is quadrate decomposition? You take an image, you split it into 4 quadrants. Then every quadrant you compute the maximum intensity value, minimum intensity value. If the difference between maximum intensity value and the minimum intensity value that exceeds a threshold T, then you split it again into just 4 quadrants. So this process continues till that difference less than T or equal to T remains constant between 2 successive iterations. This is a very simple way of creating unequal segments. So what we do, unequal granulation, consider the gray level similarity in the spatial domain of image and perform quadrate decomposition. And the splitting criteria is the difference between maximum and minimum gray level in a quadrant is greater than a threshold TG. So how do you find the threshold TG? The one thing is that we have chosen half of the interquartile range as the threshold. What is interquartile range? Interquartile range is this. Let L1 be the gray level up to which, that means 0 to L1, 1/4 of the total pixels. M is the dimension of image, M and N. So if you take multiplication, it is total number of pixels. So 1/4 of the pixels are there in this range, 0 to L-1, up to which. Similarly, L2 is the gray level to which 3/4 of the pixels are there. And you take L2 minus L1 is called interquartile range, and to take difference by 2. So TG equal to 2. That means now I split an image into 4 quadrants. I compute the difference between maximum gray value and minimum gray value. If the difference exceeds, sorry, this will be equal to sign. If this exceeds the TG, then I just split it again into just 4 quadrants. Similarly, I take again one just a small quadrant. I compute the same thing till I see that that condition is satisfied. So here TG equal to L2 minus L1 by 2. So given this granulated domain, I compute the rough entropy and I optimize and then see for which value of T. That means given a T, I get the segmentation as I mentioned in my previous one. So I take an image, I take this threshold T, and so I compute this one. So given a granular domain and the threshold T, I compute the rough entropy and then I take the optimum values, so depending on the maximize or so argument. So compute the rough entropy corresponding to every gray level and select the value for which RT is optimized as optimum threshold. So this is an example of quadrate decomposition of gray and gray formation. This is a Lena image of Lena. I don't know, many of you might have seen who are working in image processing. And when I started working at Imperial College in 1979, that is the picture we have seen in the Gonzalez and Wynn's book also. So now what is the beauty of this image? You know, if you know, it's fine. Otherwise, I'm explaining why Lena image was so used for image processing. Because this is an image where you can see so many characteristics. Number one, you have a texture, her hair. It's a textural proper image. This is a blurred image, her head and the one. It's a blurred region. This is a contrast region. That means it has got, if you take the frequency domain analysis, you have got high frequency. Here you have got low frequency. So here is it is a blurred region, this is a contrast region, this is a texture, and this shoulder represents a 3-dimensional P. We did a 2-dimensional. So it has so many. So if your algorithm works, enhancement algorithm, segmentation algorithm, edge detection algorithm, if it works fine with this Lena image, means your algorithm is much more valid as compared to other algorithm because it works with all kinds of characteristic property of in an image. Otherwise, partition image processing problem are very much problem dependent. The same image we use for remote sensing data may not be applicable for many medical data. You need to make parameter tuning. So here, this same image has so many characteristics, contrast region, blurred region, texture region, three-dimensional object, and so on. Now, if we make it say coordinate decomposition, for example, this is my all kinds of coordinates. You see that larger coordinates, smaller coordinates. Just an example I'm showing, and my red indicates the lower approximation region, and green indicates upper, which also is a subset of this lower approximation. Just an example. Now, this is the way of creating your unequal spatial segmentation. Unequal spatial segmentation. So lower and upper approximation. So with this one, we can see that if we take, let's say, a video frame, one input, all small cars, tiny people working, tiny people. So I take original image. This is a Otsu's. It's a very popular thresholding approach. It doesn't depend on the granule. This is a rough entropy I computed with 4x4 granule. That means this rectangle, 6x6 granule. Here is the proposed methodology. Here is a rough fuzzy entropy with crisp set and 6 by another granule. This is our proposed one. Now you can see that for this one, this is the best way you can see that all these segmented cars, better than anybody. Similarly, here also, nicely these are segmented. Similarly, here also you can see that one. You can see this one. Now you can ask me that, let us see this just quantitatively, because it is now visually it's okay. So now if I plot over the entire frame, this is one frame. One frame, I have shown your comparison between 5 regions. So I take the frame by frame and then segment. So I should see that whether for example, this beta value, how it is behaving. Beta should be higher. Now I take the beta index. I take all 130 to 180, so 50 frames. And I see that 6 methods. For example, if you take this one, RE4x4, that every frame the beta value improving, decreasing, improving. That means in some frame beta is good, some frame is beta worse, fluctuating. Whereas this method, you see that beta is constantly more or less consistent. Green is also more or less consistent, but beta value is less. So here, index value highest means better segmentation, and also segmentation is consistent. Better consistent over frames. Similarly, this method, which is called Otsu's method, without variation, here it is consistent. It's not fluctuating. Or on the other hand, these two, is 4x4 and 6x6. If you look at the issue, it is fluctuating. So homogeneous granules of unequal size reduce the formation of spurious segments, spurious wiggles, and therefore reduce the abrupt change of index value over frame. Same thing when you go for dB index, its value should be lower because lower value of dB index is preferred. You see that one. Here it is again jerking. If you go by the done index, similarly, so I explained the two, dB index and beta index. Now, this is my spatial segmentation from frame to frame. But if I want to track, that means I made the segmentation over every frame spatially. But if you want to make tracking, I need to make temporal segmentation. That means in the temporal domain, you also segment. What is temporal domain? You take the difference between frames. Since it is a video, you get the additional information that you can take the difference between frames. So I want to see that in the difference between frames, where should be the segmentation. So I buy from the market is very commonly used temporal segmentation based on 3 previous frames. So based on the 3 previous frames, what is the temporal segmented value? Because I have obtained the spatial segmented value. For every pixel, I have computed the regions. And the same image frame, I compute the difference from the temporal value, compute 3-point based estimation. It's called pessimistic estimation, optimistic estimation, and so on. 3-point, and you find on each pixel of input frames, and then I subtract it from the original value. So that gives me temporal segmented value. So for every pixel location, I get a spatial segmentation value in RGB plane. I get a temporal segmentation value from this difference plane, and I take its union. I fused. I get the beta shape. If I take only one component, it will be tracking, but this shape may not be extracted better because it is all temporal. So I take the spatial segmentation of the region, and then I take the temporal segmentation of the region and take the union. So I will show the merits of unequal size granule over fixed size granules. And here, once I get the segmented region, I put a tracker. So tracker signifies my segmented output. So listen carefully. So spatial segmented values and temporal segmented values in every pixel location are fused. That means I take union to result in exact shape of the moving object. Without fusion, the exact shape may not be. Because why I am taking the temporal? Because I am interested in the moving object only. I'm not interested in the static object. So that's why I'm taking the moving object, the temporal segmentation every frame. Now look at this one. The same car image, if you look at this, the same car image. This I'll take only this one car. It's moving. Others are all parked, static. Look at this one. I take rough fuzzy entropy, 6 granules, as I mentioned before. The result of 6 by 6, 4 by 4 was worse. Proposed one and then one. The same thing you'll be seeing that here. 6 by 6, see the tracker is just coming out of it. So in every frame, tracker is just coming out of because tracker signifies my moving object. But here you see that tracker is coming out of the moving object. That means if you fire based on the tracker, it may be misfire. You are again, I'm again replacing. Similarly, if you take the 4 by 4, it is even worse. Hot shoes, much better, but still you are coming first. Now, this is the proposed one, the best tracker. Tracker is, that is, as I mentioned, because every frame, the segmentation was much better than the other. And since segmentation is better in every frame, and therefore the temporal segmentation, when it united, it gives the exact shape well defined, and which is characterized by this rectangular tracker. If you go by this, see, the tracker is just coming out of the object. So this is an example where we showed that this irregular, that unequal size granule gives better result than regular shaped granule, 4 by 4, 6 by 6, and our. Here it is unequal size granule. Now, next comes to granules of arbitrary shape. So no regular shape. They are regular shape. That is, it's quadrant, square granules. But here I say the real life problem, granules are always of arbitrary shape, natural granules. So what we do here, I use neighborhood granules in RGB. Here my image is red, green, blue, and depth I have got. It's called a kinetic data set. And what I use neighborhood granules. That means I take a pixel, I compute its similarity in the color domain, and then if it similarity exceeds is a difference is lower than a threshold, then I merge. So I want to simulate. So I find that take a pixel, take its difference, The difference should be less than always some threshold. If it exceeds a threshold, I split it. So if it is less than threshold, I join them. I call them binary connected. Then again, that means I make a region growing. Region growing, this is called region growing approach. That you take a pixel intensity, you compute with these neighboring pixels, 4 neighbor or 8 neighbors. You see the difference between each of them, and if the difference is less than a threshold, you join them. That's how we go by this. So that's how we'll go by 3-dimensional spatiotemporal granule, 2-dimensional spatial one. I will explain that one by one. So it's go by region growing, and it gives you granules of arbitrary shape. And here granules obtained, I will explain, this is the beauty, lower approximation, because it is an unsupervised, I do not know the object. Usually our object tracking method, literature, as per literature, they go by background subtraction. That means you model the background first and then you subtract from the video frame so that my moving objects get extracted. But here it is not. I go by the lower approximation. That means I know it's definitely belonging. So I call it an object model. And I will use granules instead of pixel. I forget about pixel. I only use granules for object background partition. That I use granular level rule-based decision, not pixel level. And I make automatic updation of the rule base with program. And it can handle ambiguous tracking situation in unsupervised manner. What kind of ambiguity? That is, if you are overlapping objects, it can identify as 2 overlapping objects, not as one object. Newly appeared object, that means if you are tracking one object and just suddenly another object appears. So it is a newly appeared object you can track. Similarly, you can track multiple objects moving in different direction in different speed. I'll explain the characteristic part. So before that, I explained a slide, what is neighborhood in mathematical terms. So neighborhood of a point xi in the universe is denoted as a set of those points in the universe such that the distance between xn and xi is less than some phi. Of course, this is a distance function and this is a threshold which is dependent on the data set and shape and size of this granule, that is set of this granule, that is shape, is determined by the p norm distance function and the threshold, obviously. So this is a mathematical expression of a neighborhood of a point. Therefore, you can see that granules defined here around point xi with this neighborhood nx1 are overlapping, because every point you can have a granule, every point. So for overlapping data set, it is a better way of handling uncertainty. And unlike Pollock graph set, a data point may belong to more than one granule. In Pollock data set, a data point can belong to only one granule. But here is no. So one granule does not solely represent only its constitutive points. It has also points coming from other neighboring granules. Definition. So in the pictorially, this overlapping 2-class region I mentioned here. So for every point, I can have a granule. Every point I can have. So it's called region growing using color and spatial similarity pixel. So I take a pixel value picture, I compute its similarity within the distance, I compute it. So 2 neighborhood granules centered at samples x1, x2 feature space, granule shape and size. Just I'm giving a picture about a neighborhood granules. So it is all overlapping granules. So how do you compute? So we have these video frames. So I take the absolute difference from this to this, from frame 1 to frame 2, frame 2 to frame 1 to frame 2, frame 1 to frame 3, frame 1 to frame 3. So I get these differences. This is called temporal domain. Only the moving object regions come into here. So I can take any value. Now I get 3-dimensional video. Value at M, N, and P. And it will be value of in the one is a temporal domain. any value ft minus 1 minus t minus p. So ft minus t minus p is called it at tau value, temporal value at the point p. And similarly, and I computed this is with depth information only, because depth information gives the more characteristic feature for moving objects, because with moving object depth value changes. X and Y does not change that much. And I compute median at every point of the one given this p number of frames. How to compute? For every mn, I take the all p frame values at mn, I take the median. And median is a robust value. So I consider depth information and consider median information for computing. But anyway, for every mn, I have got RGB and depth value. So what is lower approximation? What do we call it? Yeah, object background, object model. So that suppose the lady is doing exercise at frame ft. ft minus 1, I take the difference, I get that value. This is the region which are moving. Then I take the previous frames, t minus 2, I get this one. Another previous frame, f3. So for p equal to 4, current frame and 3 previous frames, I get this temporal value. I take their union, intersection. If I take union, I get this. If I take intersection, I get this. Now, if I take this intersection, I can see that given all those 3 previous frames, this region is the minimum region which will be always belonging to the moving part. So I call it lower approximation. That is all the depth value information and shape intensity value corresponding to it, they will constitute my core point region values, and they really belong to object. So I consider it is a object model lower approximation. And this is the one I consider is the upper approximation, because this much of the size and shape this lower approximation can be allowed to grow. So this is my lower approximation. That means they definitely belong to the moving regions, considering the 3 previous frames. If I take 2 more previous frames, this region could be changed. So this is my lower approximation. This I extended in depth space. So given this lower approximation, I will compute all those granules over this. So before that, I explain. So what we do? So this is suppose my median plane lower approximation values. Granules extracted a lower approximation in T-frame. So for then every representative point, this some of the granules are crisp, some of the granules are overlapping, because it is a just natural granule formation. And suppose this is my centroid of this one granule. So around this granule, I go back to the consecutive previous frames and find that similarly granules again, that is the uniform region, giving a tolerance of plus minus 2. So for this granule, I get this granule in the tau domain. This is a granule, I get the granule in the tau domain. This is all. So you see that granules in the tau domain are of different size and shape. And this granule, together with this granule, they constitute what is called 3-dimensional spatiotemporal granule. So I forget everything. I only take this set tau, the set value, and I go by this same mn value, RGB and depth. So I have got corresponding to this value, temporal value set. I've got RGB value set. I've got depth value set. So for every location, I have 3 sets of values corresponding to temporal domain, that is tau feature, corresponding to color feature, RGB, and corresponding to depth feature. And with those things, I constitute a rule base, granular rule base, depending on my experience. Before that, I explain as an example the granule. So this is my input color image. This is my spatial color granule in RGB space. Look at this, different types of granule in RGB space. Similarly, the spatial color neighborhood granules, I'm explaining how do one let xi be a pixel in a frame. If xi does not belong to any other granule, then the granule over this point is, as I mentioned, spatiogranular granules, all belong to text, and where the difference between xi color and xl is less than a threshold. So x and y are spatially adjacent as determined by this threshold. If we change the threshold, then this granule size and shape will be also changed. And this granule contains those pixels which color difference is less than, and are called binary connected over spatial features. Therefore, it's called now this is the granular rule base using 3D neighborhood granules. So here you see that granules it's called temporal domain granules, RGB granules, and depth information granules. These are the different cases. Look at this one. Mobile budget. Since these are set values, I defined not belonging, partial belonging, complete belonging, and so on. Belonging. And if you see that this is the characteristic like object ideal background, this is characteristics of ideal object. That is, all features are belonging to this set. All features are not belonging. And these are other one experience based on the different ambiguous situations. Now, if you look at this very carefully, this granular rule base, these are all granules. I have forgotten now pixel intensity because I have extracted only the granules. Granules in terms of which range from spatial domain, this range, this is the range from RGB, the range for depth. Now, if you look at these granules, rule 8 and 9, same feature. That means same temporal value belonging, same aj value, this, I got in background and object. Same features, but our decision is one is background, one is object. So I call it inconsistent granules. Others are consistent granules. That means either they characterize a background or object with different sets of features. Now, so therefore, our objective will be that these two inconsistent granules should be less fired. So given an unknown object consisting of sub-granules, we'll see that the granules constituting regions should not be classified, or if you classify, it's a list number or classified by this granule number 8 and 9. Accordingly, if this inconsistent granules is fired and this number such firing inconsistent value is larger as determined by some coverage factor. Coverage factor you can define in various ways. For example, you can define as a total unambiguous granules divided by total granules. So it will be 10 by 12. And you have to see that your denominator should be less. That is, unambiguous granules should be less fired. Otherwise, you update this conditional attributes. What is the conditional attributes here? If this is this is this, they will do this. So we made these granular changes, this change in the conditional attributes of the rule base. If the inconsistent granules, inconsistent rules get fired more. And then how do we do the upgradation? For example, these are my different granules with granules moves with floor estimated, object granule with changing depth, different 10 characteristics based on our experience. So form granular rule base for tracking, update rule base with flow graph. Whenever I see that, my number of times the inconsistent granules fired more. So number of times it has fired more as determined by the coverage factor of the rule base. I update the rule base. That means the consequent antecedent part, conditional attributes with flow graph. So what is the beauty of the flow graph? This flow graph is called integration, the intelligent automation, automatic updation. Why is it called automatic updation? That is, I make the intelligent in the sense that neither the ranges of all features for an object is changed, not the ranges of all objects at a go. That means I only update a particular feature which one is required as determined by my flow graph. Very carefully note this. Suppose this for an object there are got 8 or 10 granules constituted. So the 3 to 4 granules get updated. So I want to change the corresponding which feature, not the all features. That will be determined by my granular program. And granular program will say that you only update the particular feature, this not all the features, or not all for other also features. That's why it's called intelligent one. So I made it's called granular program because it maps the decision paths of the granular rule base. And because of this, updation is done for a particular feature only when required instead of every time and all features. That's why it's called intelligent updating. So this is our methodology. If you look at this, after that I will take a break. So you take unsupervised initial labeling, you have got p-frames, you compute the three-dimensional spatial color granules, then compute one-dimensional color granules, one-dimensional depth granules, one-dimensional temporal granules, you form the rule-based object model, you find the rule base. And also use the same for flow graph. Then you take an unknown, you compute the same spatiotemporal granulation, compute one-dimensional this, and you match with the rule base. And you segment the foreground image depending on the decision of the rule base and compute the coverage of the rule base. If the rule base is satisfactory, then track the segment. If it is not, then update the rule base using flow graph. That means an upgradation is done from this original flow graph, and then again you put it in the rule base. That's how the system works. Now look at this. The guy was doing exercise with a two. That means he was moving his two hands. So basically two objects now overlapping with granulation. If I took the flow graph updation, look at the situation. See, two objects are again I'm showing. He was moving two objects, two hands. So tracker is able to detect two moving objects separately, though they are overlapped. The other tracker can consider them as one object, but here it is not. I'm showing again. Yeah. Similarly, for showing the significance of upgradation, the lady was doing exercise with her right hand. But you see that suddenly left hand she started moving, but the tracker is not able to track it again. On the other hand, if you see that when it succeeds rule-based updation, yeah, she was doing right hand, but the suddenly left hand she tracked, and you see that tracker is able to track it. So this is because of the program updation. Similarly, different persons are moving in different direction and different speed. So it's a reflection of window. This is a depth value. So since you have taken depth value, that's why the shadows is not getting tracked. So depth value. So these are all unsupervised with granulation. And if you compare with, because there is an unsupervised, so we compared with some partially supervised. Obviously, partially supervised will give better result, but still you can see that when you compute in terms of time and the centroid distance between the object, that means the tracked object and their original value, source value. If you go the ground truth value, you take the difference. CD value is least, here highest, except this. CD value is the second lowest. Similarly, time of computation from here, it is lowest. Here it is 2.2. Here it is lowest. Similarly, if you take the other image, same thing. So comparison are required made with the partial supervised, where initial manual labeling was required for them. But in our case, it is completely unsupervised. So let me take a break for 15 minutes. Okay?
Yes, sir. Thank you, sir.
Yeah.
So we'll meet after 15 minutes.
Yeah.
At 4:35.
Okay.
Okay.
Okay. Thank you.